So today, we're diving into a really cool system designed by Khalid Fahad AlTurki. At its heart, it's a predictive system for air conditioning. Think of it like a crystal ball for our buildings, one that's designed to see a failure coming long before it actually happens. And it all starts with a feeling I'm pretty sure we all know a little too well.
Right? We have all done there. It's the most sweltering, hottest day of the summer, the one day you absolutely cannot live without your AC. And that is the exact moment it decides to just give up. It almost feels like a law of the universe. But what if it didn't have to be that way?
The reason this happens so often is actually pretty simple. The way we handle maintenance right now is just broken. We are completely stuck in a loop of just reacting to problems after they happen. And that approach is not just inefficient, it's incredibly expensive. And this all boils down to a really fundamental difference in philosophy. On one side, you've got reactive maintenance, which is basically the wait for it to catch fire method. We wait for a catastrophic breakdown and then we scramble to fix it. But on the other side, you have predictive maintenance, which is all about fixing something before it breaks, because you're actually listening for the warning signs. And believe me, the cost of just waiting around is huge. It's not just about being uncomfortable. Sudden shutdowns can bring a business to a grinding halt. Technicians often end up replacing perfectly good parts just because it's time, which is a complete waste of money. And maybe the biggest hidden cost? A unit that's about to fail wastes a massive amount of energy just trying to keep up before it finally dies. Okay, so if the old way is so clearly broken, how do we build a smarter one? Well, this is where it gets really interesting. This is where machine learning comes into the picture. As it turns out, AI is the perfect tool for this exact job. So why is AI such a perfect match here? It really comes down to three things. First, we already have all the clues. Modern AC units are packed with sensors, giving us tons of data. Vibrations, temperatures, you name it. Plus, we have all their maintenance history. Second, the potential value here is just enormous. The savings in cost, in energy, and just in keeping people comfortable are huge. And third, and this is the magic part, the system is designed to get smarter and more accurate the more data it sees. And the business case for this is so powerful. We're not talking about some tiny little improvement here. The goal is to get up to a 30% reduction in those unexpected, day-ruining shutdowns. That is a massive, real-world impact. So how exactly does a machine learn to become a kind of digital mechanic? Well, it's all about teaching it to turn a whole flood of raw data into a really clear, simple diagnosis. The system is basically a detective, and it looks for digital clues from three main places. First, you've got the live data pouring in from sensors, stuff like weird vibrations or a compressor that's running too hot. Then you add in external context. Is there a massive heat wave going on? Is the building packed with people today? And finally, you layer on the device's own history. How old is it? When was it last serviced? All these clues together paint a really detailed picture of that unit's health. Now, all those clues, all that data, it all feeds into one single core prediction. The model is constantly asking itself one question. Based on everything I'm seeing right now, is this specific unit likely to fail within the next 14 days? That simple yes or no is what drives the entire maintenance schedule. But making that prediction, it is a super delicate balancing act. On the one hand, goal number one is you absolutely cannot miss a real problem. You have to catch every single unit that is genuinely about to fail. In the world of machine learning, that's called high recall. But on the other hand, you can't be the system that cried wolf. You have to avoid false alarms that would just overwhelm technicians and make them stop trusting the system. And that goal is called balanced precision. Okay, so that's the theory, but how does this digital mechanic actually get built and plugged into the real world? Let's take a look at the blueprint. The thinking actually happens in two places at once. Some of it happens right there on site, in the building, what we call the edge. This is for the fast reflexes, If a sensor suddenly goes haywire, it can send an instant alert. But the really deep learning, the heavy-duty analysis of long-term patterns across thousands of AC units, that happens in the cloud, where you have all the computing power you could ever need. And you don't just, flip a switch on a system this complex. No way. The plan here is a very careful, phased rollout. You start small with a test on just a couple of floors, a minimum viable product. Then you move to a controlled experiment, comparing floors using the AI to floors that aren't. And only after you've proven it works do you start a gradual expansion. So all of this leads to the ultimate goal: smarter buildings and, frankly, better living for all of us. But it's also really important that we talk about the real-world impact and, of course, the challenges that come along with it. And this is probably the question on your mind right now. But can't an AI just get it wrong? And yeah, of course it can. No system is ever going to be perfect, which is why having a rock-solid plan to manage that risk is absolutely crucial. And this system has those safety checks baked in from the very beginning. It's designed for constant monitoring, not just of the AC units, but of itself. It's always looking for weird changes in data patterns. It has automatic alerts for things like a broken sensor or a bad data feed. And most critically, there's a plan for regular retraining. It's like sending the AI back to school every so often to keep it sharp and up to date. This quote from the author, Khalid Fahad AlTurki, really just captures the whole vision perfectly. He says, "The goal is to create buildings that anticipate our needs, saving energy, money, and ensuring our comfort." See, it's not really just about fixing machines. It's about creating better spaces for people to live and work in. And that really leaves us with one final big question to chew on. We've just seen how this kind of thinking can totally transform our buildings. So what else in our world should we be teaching to think ahead? Thanks so much for joining me for this explainer.